Assalamu alaikum dear students, to our new lectures in hydraulics and irrigation engineering. We are going to cover now the irrigation part of this lecture, and this lecture is basically about the elementary concepts about the canal headworks, selection of their sites and layouts, weirs and barrages, and various components and functions of canal head regulators. These are the contents of our lecture today, and the books that we are covering or you should refer to with respect to the contents that are present in this lecture are the Irrigation and Drain Engineering by Peter Waller and Irrigation Engineering by R.K. Sharma. These are the books that we are mostly going to follow with regards to the irrigation part. The contents of this presentation, as you can see here, are the following. First of all, we are looking at the canal headworks, what they really are. How are we going to select the site and the layout of a particular headwork? And then we are going to move to the weirs and barrages and the canal head regulator. If you remember, in the very first lecture of this subject, we covered or we went through 2 or 3 practical examples of irrigation engineering. One of them, if you remember, was Ghazi Barota project here in Sawabi and Mardan area. And if you remember, we looked at different diagrams where we looked at the channels and we looked at the head regulators and the fish ladders and the under sluices components. So that was only an introduction to the irrigation part. Although that particular channel is used for the power purposes for generating hydroelectricity, but mostly a head regulator or a canal headwork, whether it's for irrigation engineering or whether it is for the hydropower production, they follow more or less the same design processes and the same kind of structures. So first of all, what really is a diversion headwork? Diversion headworks are basically structures which are used to raise the water level so that we can then push water towards a particular canal or a particular channel. And that water can then be used either for hydropower electricity production or for irrigation purposes. The main purpose, in addition to increasing the head and diverting the water, is also to provide water in a continuous regulated way, which means that the water in the canal or in the channel is according to certain requirement. You see, we have a discharge requirement. For example, let's say we have to irrigate a particular area where we know that the crop requirement is something like maybe 200,000 hectare feet or any kind of water in terms of the cubic meters per second value. So we have to ensure that this canal is producing that or conveying this amount of water, not producing but conveying this amount of water in a regulated way. In addition to discharge or the quantity of discharge, it also the diversion headworks also ensure that the water is mostly silt free. There is no silt in the canal, so that when the water reaches to the tail end, we do not have a problem of siltation in the channel. So we try to install certain structures which kind of stop the silt from entering into the channel, and we'll look into these structures as well. This particular subject is related with the introductory part of the hydraulic structures. We are not going into the design of these structures because this is then a topic of MS level, where we study design of hydraulic structures, and then in design of hydraulic structures we go into the rigor of the design of these structures, whether they are dams, they are weirs or barrages or any other component. In this particular lecture at undergrad level, we need to ensure that we know what are the diversion headworks, what are the objectives of a particular headwork, what are different components of hydraulic or the hydraulic structures of different headworks and what are their purposes. So that would be mostly the content of this lecture. As I said, the objectives of a diversion headwork is to raise the water level at the head of the canal, and this raising of water level will give enough energy for the water to reach to the tail end. Then it also form a storage by constructing different kinds of embankments on both banks of the river, and this ensures that the water is available throughout the year. You see, even when you would have observed while going through or going on the motorway from Peshawar to Islamabad, you would have observed the Ghazi Baroda project, and you would have seen that no matter whether it's the winter season or the summer season, there is a flow in that particular channel. So we ensure that we have embankments on the headworks where we can store water so that that water can be pushed into the channel even when the water in the river is not that much. The objective is also to control the entry of the silt and also to control the deposition of silt at the head of the canal, and then to control the fluctuation of water level in river during different seasons. And it is important to maintain the water level, because if the water level is maintained, then we'll be readily sure that the water is reaching the tail end. Otherwise, we would be having a problem of water not reaching to the people where it is required or to the areas where it is required. If we look at the requirement of the site for diversion headwork or the layout of it, it should be kept in mind that the area should be so selected that the river at that particular section or at that particular site is straight and narrow. We need it straight because we need to divert water and we want most of the water to enter into the channel, and we want it to be narrow because we kind of targeting the higher velocities. As you know, if we have lesser area, the velocity would be greater. If we have greater area, the velocity would be lower. So we kind of target the areas where the river section is kind of narrow, so that we can have enough velocity for the water. The river banks should be well defined, and this is important because we do not want the water to enter into the adjoining areas. So we have that particular defined level, and we know that the water would be within these boundaries. The site should also be selected in such a way that we do not have a lot of valuable land coming under the water. So not a lot of water should be submerged, and the natural banks of river should be maintained. The elevation should also be higher than the area which is irrigated, which is only understandable. The higher the elevation is, more energy would there be in the water. Both the hydraulic rate line and the total energy line would be greater, and it would be kind of easier to transport water to even the most further part of the catchment or to the area where it is to be transported. It is also important that these areas are readily accessible by roads or any other kind of communications. If it is easily accessible, it would be easier to transport the construction material. It would be easier to transport the different machinery that is required into the diversion headworks. For example, the larger gates, which usually stop water from entering a particular area. So a lot of heavy machinery that is needed in the diversion headworks need to be transported there, and we therefore look at the area so that it is accessible by different ways of communication. Material of construction should be available in vicinity of the site. This is also important requirement. Otherwise, we will be consuming a lot of resources in transporting the construction material from, let's say, far away places to this diversion headwork. So more or less the construction material should be easily available and available in the vicinity of the site. Ideally, the last point, this is an ideal point, but it's not necessary that we select the area which is closer to the command area where we are going to irrigate the area, because sometimes, and you would have seen the examples in our earlier lectures, the diversion headwork is hundreds of kilometers away from the area where we need water. So there is a lot of distance between the diversion headwork and the command area for irrigation. It is ideal that the place is near to the command area, because this way we can ensure that the evapotranspiration or evaporation losses are minimum, or the transmission losses are minimum. But it's not a necessary condition. So these are few conditions which are important when you are going to select the site for diversion headworks. The most important part of diversion headwork are weirs and barrages, and the difference between the two is very clear. We would have, I think, discussed it earlier in the classes, but weirs are the structures which have a raised crest level, and the thing that makes it different from the barrage is that most of the water that is stored in weir is stored because of this raised crest level. So there is a very small portion of water. For example, if you can see here in this figure, a very small portion of the water which is basically stored by the gate. Most of the water, for example, if you look at this section, most of the water here is stored by the raised crest level. So this amount of water which is stored by the raised crest is far greater than the amount of water which is being stored because of the gates or any kind of shutter which is installed on top of the crest. In case of the barrages, this is vice versa. In case of barrages, most of the water is stored by the gates that are installed on the crest level, while a smaller portion of water is stored because of the crest that is being erected. So these two, this is basically the main difference between the weir and barrages. Except this particular difference, which is just a difference in definition, more or less the working of both the structure is the same. So we are going into the parts of different hydraulic structures which are associated with the weirs and barrages. As we said earlier, that the layout has to be considered or selected in a careful manner. The parts, or let's say the components of a particular diversion headworks are the following. We have a weir portion, where either we install or erect a weir or a barrage. Then we have undersluices. These undersluices make sure that the water that is entering the canal or the channel is silt free, or mostly it is entering into the channel in a regulated way. We have divide walls which are installed between let's say the weir and the fish ladder, if there is any. Important part are also the river training works, the fish ladders, the canal head regulators, another important machinery like the hydropower equipment, the turbines, the pumps if they are needed, and also the silt regulation works. We are going into a few of these components in detail in the following slides. First of all, if we look at the weirs, we basically divide weirs into these three types. We have either masonry weirs or a rock fill weirs, and mostly lately we are also seeing a lot of concrete weirs which are being constructed in different projects. But earlier weirs, if you look at the weirs which have been constructed let's say 30, 40 or 50 years ago, most of them were either masonry weirs or rock fill weirs. And we are going to look at their structures and their figures. You see, this one is basically a masonry weir with vertical drops. What we mean by vertical drops is that this weir, and this is, by the way, the section of a particular weir. You see, we have most of the water here is stored by the weir itself, and very small portion of the water is being stored by this gate or the shutter that is being installed here. The walls of this weir are almost vertical, but it is possible that we have kind of sloping walls on the downstream and upstream side. If we have the sloping drops or the sloping walls of the masonry weirs, then we kind of ensure that the side on the upstream side is more the slope of the walls on the upstream side is more than the slope on the downstream side. This is to ensure that we do not have seepage inside the wall, or let's say the phreatic line is maintained within this weir body. On either side of this weir, you see these upstream cutoff walls and downstream cutoff walls. You see these small structures here, both upstream and on the downstream side. The purpose of these cutoff walls is that we do not have water which is seeping through on the upstream side and then traveling in this direction to the downstream side. So we kind of ensure that the water does not seep through the structure itself. Because if water does seep through, and let's say it is entering into the upstream side, getting out of the downstream side, then it is detrimental for the structure, for the whole structure, whether it's a weir or a barrage. So it is very important that we have this impermeable layer here, and then in addition to this impermeable layer, we have these cut-off walls on the upstream and downstream side. We need to ensure that we have different structures. For example, you see here we have this rubble apron here on the downstream side and a puddle on the upstream side. These structures are installed so that we can somehow dissipate the energy that the water usually would get when it is going from the upstream side to the downstream side. If you remember, we looked into the hydraulic jump in the lectures before the midterm, and we said that during hydraulic jump water gains a lot of energy, and to get rid of that energy we kind of either have structures like these structures which kind of dissipate the energy, and the structure itself is saved from this higher energy. So these rubble aprons are installed for this particular purpose. You see, as I said earlier, if we have sloping aprons on the rock fill weirs, then we need to ensure that the slopes on upstream side is greater than the slope on the downstream side. If we have this kind of structure, the water would need longer distances to cover or to reach from the upstream side to the downstream side. You see, this is more or less understood that water would be seeping through the structure. What we need to do is that we need to ensure that this water does not reach this downstream part, and it is somehow maintained within the body of the weir or a barrage. So let's say if you have water, for example, if you follow the line here, if water is entering in this direction here, then we kind of provide structure inside this barrage or weir body that this line is discontinuous. It is not a continuous line which is showing up somewhere here. So this has to be avoided. What we need to do is that this water, once it enters the dam or the weir body, it somewhere stops inside the structure, We collect it maybe somewhere here, we collect this water here, and then we safely transport this water to the downstream side or any other area. But we make sure that this is not the case, that the water is reaching to the downstream side and then showing up there. Because if it does occur, if the water does reach to the downstream side, what would occur is that we would be having higher uplift pressures, which usually occurs in this direction. And these uplift pressure are usually so high that it can cause considerable damage to the structure itself. So this has to be avoided in any ways. Lately, we are also seeing concrete weirs which have been installed in different areas, and concrete weirs are important in a sense that their construction is easier than the rock fill weirs or any masonry weir. They are usually installed as a monolith structure. You have one big structure which is installed, and it is the concrete is poured in one go for the whole structure. And the whole structure is considered as one monolithic structure. So you see here that this whole structure, starting from the upstream side to the downstream side and then the weir itself, this whole structure is one complete monolith which is constructed either in one go or maybe in portions, but at least the structure is one whole. The importance, or let's say the advantages of concrete weirs, is that they are usually quite heavy, and this gives us enough gravity forces which are occurring in the downward direction. So these gravity forces ensure that the weir stays in its place, and mostly the weight of the weir is enough to make the whole structure stable. Next are then the barrages. Barrages, as I said earlier, are mostly the weirs installed in a way that we have a gate or a shutter on top of the crest level, and this ensures that most of the water or most of the ponding is done by the gates. Very small portion, or in some cases even there is no water that is being stored by the crest itself or the lower portion of the weir, and most of the water is stored by the gates that are installed on top of a particular weir. You see here is this the cross section for a particular barrage. You do not see any kind of crest in here. It's mostly a level structure starting from the upstream side to the downstream side. You do see, as in the case of weirs, you do see the upstream cutoff walls and the downstream cutoff walls. In this case they are called the sheet piles, but they serve the same purpose as in the weir. You can call them sheet piles or the cutoff walls, but the purpose of them is that it discourages water from entering to the structure which is directly beneath the barrage structure. We do see here the gates which are installed here. So the gate in this figure is this one, and we control this gate from top of the crest level here. So we either raise the gate or lower the gate. Mostly the mechanism is installed on top of the crest level here. We have larger pulleys and rope structure which kind of move the gate in either in the upward direction or the lower direction. You do see here that the pond level for the maximum level is somewhere here. So we can store a lot of water with the barrages, and most of the water is stored by the gates of the structure. You should consider here that in case of floods coming in a particular stream or river, the mechanism of working for the weir and barrages would be very different. Once a flood comes and let's say we have a weir there, weir is mostly uncontrolled structure, which means that once water level reaches top of the crest, it would start flowing downstream. There wouldn't be any kind of control once the water level exceeds the crest level. In case of barrages, we have that option where we can store water even above the crest level, because the gates can give us that flexibility there. And this has a very big impact on the downstream hydrograph. You see, if you have a weir and there is a flood situation, the hydrograph, once the water exceeds the value, or let's say exceed the level of weir, the hydrograph would be more or less the same as the original flood level. So the peak wouldn't be that much different in case of weir. There would be delay. The delay would be there in terms of the peak occurring at a particular time. So if there is a weir, the peak of the flood would occur maybe 1 or 2 hours later. So there would be this 1 or 2 hours with you where you can take some certain precautionary measures. But the peak wouldn't be lower. It would be more or less the same peak if there were no weir, so to say. In case of barrages, we have this flexibility that not only the peak would be delayed, but also this peak would be lower than the peak of the flood if there were no barrage. So this is also a big difference between the two. That it not only the barrages not only reduces the peak, it also delays the peak. In case of weirs, it only delays the peak, and the peak does not change in terms of its intensity. Here I've listed the main differences between the weirs and barrages. So you see that the barrage has a lower crest value as opposed to the weir. As we said earlier, ponding is mostly done by the gates in case of barrage, while in weir it is again mostly because of the raised crest that we store the water. The entire length of barrage is gated, which means that throughout the section of the barrage you have gates installed throughout the length of the weir or the barrage. In terms of the shutters, in terms of the weirs, the shutters are only part of the length. So maybe if you have, let's say, almost 500 meter of width of a river, part of it would be covered by the shutter, but not the whole 500 meter would be covered by the shutters itself. So this is also a big difference between the two. Barrages have the gates which cover the whole width of the river. In terms of the height of the gates, barrages are usually having gates which are greater in height as compared to the weirs, which are usually smaller gates which are either 2 meters or less than 2 meters. Rest of the differences, you can look at these differences yourself and also can consult the book there. For example, this particular difference, perfect control over the river flow, as I discussed in the previous slide. In case of barrages, you have this control available to you because you have the gate and you can lower or increase the gate level any way you want or according to the downstream conditions or the requirements. In case of the weir, once the water passes the crest level, then there is no control over the water flow. And just assume that if you have 2 or 3 weirs installed in series, and let's say all of them are going above the crest level, then all of a sudden you would be having a flood which is 2 or 3 times greater than the original flood, because each weir is now contributing to the flow, each weir has stored certain amount of water, and now that amount has increased from the crest level. So you have a situation where the water level is higher than the original flood value. So these are the differences between the barrages and weirs, and one has to consider all these differences before taking a decision whether we should go for a weir structure or for a barrage structure. Barrages are usually costly. This is one disadvantage of barrage, because we have these mechanical gates which are being installed there. These gates are usually very big, and they have the cost of them is quite high, because you have to store water, and you have to store water which has a lot of pressure energy there. So you need to install gates which are not only bigger in size but also strong enough to resist the pressure of water. So they usually, and gates are usually the structures which in diversion headworks consume most of your economic resource. This is one disadvantage of the barrages. Next are our river training works. These are very interesting structures which are usually installed in a diversion headwork. Just upstream of the diversion headwork, these are installed there, and they include the guide banks, the marginal burns, and the spurs and groins, which serve different kind of purposes. The main function of the river training works is to ensure that the smooth and axial flow of water is maintained. You see, we need to have this axial flow of water towards the regulators or towards the channel, so that maximum velocity can be achieved, and this maximum velocity, as I said earlier, can then be used to irrigate the areas which are far downstream from the diversion headwork. Guide banks are constructed just upstream of the diversion headwork. They are constructed there so that we can protect the important structures from erosion, and the water entry into the regulators is smooth and axial. It not only protects barrages from the effect of scouring and erosion, it also provides a straight approach towards the barrage. So these guide banks, they ensure that the water is flowing towards the barrages, and that the velocity is maintained in these sections, so that there is no scouring or erosion in areas which are nearer to the diversion headwork. These two things are already discussed. The tendency of changing the course of river, it controls the tendency, because you see, and you would have observed that usually depending upon the season, the river changes its course depending upon how much water is there in the river. Sometimes it would be flowing in one particular section of the river or in the floodplain, and then in other season it would be flowing somewhere else. So the guide banks ensure that the course of river is maintained, and they are in a particular section of the river which is needed. So this is also an important function of the guide banks. And as I said earlier, the velocity is also maintained by these guide banks. This is a particular shape of the guide bank. You see here, we have the main structure is somewhere here, and we'll see the different parts of this structure. But these guide banks make it sure that the river flow is within these two boundaries that are defined here. Marginal berms are also erected within the whole structure of diversion headwork. These are usually the earthen embankments, and they are constructed parallel to the river bank, either on one side of the river or maybe on both sides of the river. Their top width is usually ranging between 3 meters to 4 meters, but this is just a value which mostly depends upon the condition of the river. So how big the river is, how much water is being diverted to the channel. So it all depends upon the particular layout and particular section of the river. It's not in any ways a guiding principle that it should be between 3 meters and 4 meters. The side slopes are more or less a kind of guiding figure. So you see the side slopes on the river side is generally 1.5 to 1, and then on the other side, that is on the side where there is population or other important structures or buildings or roads or any kind of other structures, it should be 2 to 1. So the slope on the river side is smaller as compared to the slope on the countryside. As is understandable, the guide or the marginal bund, the main purpose of the marginal bund is that we want to ensure that the flood water or the normal water, the storage water, it does not enter the areas where there is any kind of population or any kind of structures there, the roads, the buildings, or any other kind of structure. It also helps us in controlling the seepage in the areas. These marginal bunds ensure that the water is within those boundaries or the boundaries of the river, which in turn ensure that the areas which are near to the diversion headworks are not ponded with the water, so that the agricultural land can be saved if there is any kind of, let's say, agriculture area nearby the diversion headwork. Also during the flooding level, the flooding season, these marginal bunds make it sure that the areas are safe from the increasing water levels. This particular diagram gives you an indication or an idea about the marginal bund. You see, this is the guide bank. This guide bank ensures that the water enters a particular diversion headwork in an axial way. This, on the other hand, this marginal bund, it makes it sure that the water, even if it enters into this area, it does not go out of these boundaries, and maybe, let's say, if you have any kind of structure here, or maybe if you have an area which is being irrigated, so these areas are not flooded because of the water level of the river. As I said, this can be installed depending upon the condition. It can be either on one side of the river or either on both sides of the river. It can be installed here. So these marginal bunds are basically for the protective purposes of the areas which are beyond the boundaries of the river. Another important structure are the spurs. Spurs are also installed just upstream of the river diversion headworks. There are basically two kinds of spurs that are being considered. Either they are temporary structures or they are permanent structures. Temporary structures are only installed or erected in flooding seasons, and in flooding season they do their job, but otherwise they are either dismantled or not looked at in a particular way. These are permeable structures, so the water can seep through them, and they are installed in a particular angle, either to the upstream side or to the downstream side, and we'll see these angles in a couple of minutes, so that the water again can be directed toward to the diversion headwork. The length of these spurs, it basically depends upon the total width of the river, and in case if there is a curve, and usually there is a curve, spurs are installed in the areas where there are if there is a curve in the river flow, and we install these spurs so that the water can be directed towards the main river course. So if there is kind of curve there, then the length of the spur would depend upon this radius of the curve. What is that radius of the curve, and how large or small the curve is. Not only in terms of the diameter, but also in terms of sharpness, we need to look at these curves. In any ways, whatever the length of the spur is, usually we have three kinds of spurs. Either they are bamboo spurs, the timber one, or the boulder ones. The main function of the spur is to break the velocity of incoming flow, because the river, if there is a curve in the river, and usually we do see that inside of the curve the velocity of water would be greater as compared to the velocity of water on the outside of the curve. So we need to break this velocity, and as I said earlier, this is installed before the diversion headwork, quite some distance before the diversion headwork. So we are not very much interested in the velocity of water at this particular section. So we can somehow reduce the velocity of water. This velocity, this breaking the velocity of incoming flow, makes it show that the pockets that are created, the pockets of water that are being created, most of the sediment can be settled in this area. So the water that is then getting out of these pockets is mostly silt free. So although it is not a silt excluder or a silt ejector in itself, but it also helps us in reducing silt from the river water. These are two particular diagrams of the spurs. On the left hand side you see the bamboo type, and on the right hand side you see the timber type. You see, what we usually do is that we have piles of bamboos which are being installed, and the hollow section of these spur area is then either filled with sand or any other kind of material. The bamboo types are usually suitable for the smaller rivers. They are not very much effective in larger rivers. But they do work in a smaller river where you do not have a lot of velocity, or let's say the curve is not that much sharp. So it would do its job there. So we have, if you can see, if this is our river bank, then these are installed diagonally in this direction with between 60 to 75 degrees. They are inclined towards the upstream side. The flow of water is, in this particular diagram, is from this to this side. You see the arrow here shows you the direction of flow, and this spur is installed inclined to the river bank between 60 to 75 degrees here. The disadvantage of these kind of structures is that they are, first of all, they are temporary structures, and they need frequent repairs. So almost after every flooding season you have to look at them, and you have to maintain them almost every year. The timber types are usually installed in a larger river where you have higher velocities, and you need structures which can break those velocities. They are also installed in comparatively larger rivers, and the spaces between these timbers are usually filled with the boulders. So as compared to the bamboo type, where the hollow areas were filled with the sand or other loose material, in case of the timber type, they are usually filled up with the boulders, which are heavy boulders, so that they can be maintained for a long period of time. With respect to their maintenance, they do not need that kind of attention as the bamboo type would need, but still they are again permeable, and they can be temporary structures just upstream of the diversion headwork. The boulder spurs, on the other hand, mostly in Pakistan and in the areas that we usually observe in KP. For example, in the northern areas, if you have the chance to observe the rivers there, you have these spurs which are usually, so these are basically big boulders which are enclosed by the kind of GI wire net. They are usually in circular shape. We have this network of wires, and these wires contain large boulders, and these usually serve the purpose for us. They are also important because they work very efficiently in larger rivers which are, let's say, the velocity of flow is very high, and also when the width of the river is bigger as compared to the previous cases. The angle of their construction is the same. They are almost 60 to 75 degrees upstream in the direction of towards the direction of upstream water. And if you see the section, as I said earlier, they are circular in shape. You have these large boulders which are being wired through these GI wires. The boulders inside this section are usually 30 kgs to 50 kgs in mass, and the diameter of the GI wires is usually 4 mm. So this is the diameter which ensures that these heavy blocks, they remain in their place and the incoming water is not dislodging all the structures. Another important structures that are usually installed in the diversion headwork are the groins. Groins are in terms of function, they serve the same purpose as the spurs are serving. That is, they break the velocity of the water. They are installed along the curves, and their angle of construction is also the same, 60 to 75 degree along the bank, in either towards the upstream direction or to the downstream direction. And their inclination towards either upstream or the downstream direction makes it possible to either attract the water towards the banks, and hence the name the attracting groin, or to repel the water from the banks towards the main river, and then they are called the repelling groins. So this is only depending upon what kind of inclination you are giving to the groin, so that the water is either attracted towards the bank or repelled from the banks. The thing that makes it different than the spurs is that they are impervious in nature. Water is not entering inside the groin structures, and also they are permanent structures. In case of spurs, we said that they are usually temporary structures, and after every flooding season, or after maybe as the case may be, you have to dismantle them or install them somewhere else. In case of groins, they are permanent structures and they are impervious. These are the three types of the groins. As I said, depending upon what is the orientation of the groins, whether it's up towards the upstream side or to the downstream side. So we will see how they act once they are installed. You see here, this is a particular river or the curve of the river, and this is a particular groin which is installed here. In this case, you do see that this is installed in this direction, and it is 60 degrees oriented towards the downstream side. And this makes it attracting groin. It makes, or let's say the type of this groin is then called attracting groin, because the water is attracted towards these curves towards the bends side. So this 60-degree is in the direction of the downstream side. If L is the length of this groin, then the spacing between the two groins should be 2L. So that this is what it is maintained here. The distance between two groins should be 2L, where L is the total length of a particular groin. On the right hand side, you see the repelling groin. The repelling groin, as you can see, the arrows here is showing the direction of water. They are now 60 to 70 degrees in direction of the upstream water. Here we see they are in the direction of downstream water. Here they are in the direction of upstream water. They kind of direct water towards the inner part of the curve. So they are, in this sense, they are called the repelling groin because they repel water from the curve side towards the main river channel. Deflecting groins are then third kind of groins. They are almost 90 degrees to the river banks. So you see this is almost making a 90 degrees here. And they deflect water from the banks towards the main channel. These are the differences between the spurs and the groins. As we said, spurs are permeable, the groins are impermeable, they are temporary structures. The spurs, on the other hand, groins are the permanent structures. So these are few differences between the two structures. As I said earlier, spurs are usually installed in smaller rivers, while groins are considered for a larger river where you have larger volume of water passing through a particular section, or maybe if the velocity is high. So you see here, groins are suitable for higher velocity, while spurs are usually installed in the areas where the velocity is either low or medium. These are the main differences here. Another important structures are the fish ladders. Fish ladders are installed either on the side of the diversion headwork or right in the middle of the diversion headwork. And the purpose of them is that we kind of provide a way for the fish to move from upstream to the downstream side. Otherwise, if there are no fish ladders, then somehow the natural habitat of the fish would be affected, and their usual traveling between upstream and downstream side in different season would be affected. So fish ladders are provided so that the fish can move from upstream to downstream or downstream to upstream, whatever the case may be. This is a plan view of a fish ladder. So you have these kind of structures, the divide wall, and then these small structures of wall which kind of make sure that the water is flowing from one section to another. This is the section of this particular structure, and the water is A is on the upstream side and B is on the downstream side. So depending upon the season, the fish can move from either this way to this way, or from the downstream side to the upstream side. These are particular some diagrams, or let's say some pictures of fish ladders. You see here we have the upstream side here and the downstream side here, and then these are the structures which makes it possible for the fish to move from either direction towards the other. Silt regulation works are another important structures in a diversion headwork. These are the structures which control the entry of silt into the channels or the canal. This is important. As I said earlier at the start of the lectures, we kind of reduce the silt load from entering into the channel so that the water that is going for the irrigation is mostly silt free. Usually we have two kinds of structures here. Either they are silt excluders or the silt ejectors. Silt excluders are installed just before the channel where, so the water has passed through the head regulator and now it is going through to the channel, and we have these silt excluders which reduce the amount of silt entering into the channel. This particular diagrams gives you an indication of how the silt excluder works. These are the sand sluices. This is the dividing wall here. You saw in the previous diagram that you had a dividing wall, and this dividing wall was housing a fish ladder. So on one side you have these sand sluices, and these sand sluices makes it sure that the water that is entering into the head regulator is silt free. Silt ejectors, they are also called the silt extractors. These are usually the structures which serve the same purpose as silt excluders. These are the structures which are installed at the bed level of the river just before entering into the channel, and the bed level structure makes it possible for us that the silt is sedimented in that particular area, and then we can transport it to a particular area where the silt can be ejected from the main course of the structure. So these works are constructed on the bed of the canal, in the little distance from downstream from the head regulator. This is what they are installed here. And this would be clear when you look at the section map of here. So you see this is our section AA of this particular channel. This is a channel just before entering into the silt excluder. So the normal bed width and the sloping sides of the river. And then this is the cross section right at the silt excluder. So you do see that this is now the bed of the river. It is made in such a way that the water is sloping towards the silt excluders. The silt is settled in this particular area, and then from this area the silt is excluded from the river network to any outfall escape. Head regulator are provided at the head of the off-taking canal, and they usually serve the purpose that they regulate the supply of water entering into the canal. It also controls the entry of silts and also controls water to enter into the regulated channel during the flooding season. So you see we have this these structures, we already looked into them, the marginal burns and the guide banks. The water is directed towards the off-taking canal. We have this divide wall, the fish ladders, and then the proper weir here is installed in this particular area. So canal head regulator is provided at the head of the off-taking canals. This is our off-taking canal, and this is our head regulator which is installed here. So the head regulator makes it possible or ensures that the water entering into the canal is of particular amount. So any particular discharge of water is maintained because of the head regulator. This is the diagram that we looked into in the very first lecture. This is a Ghazi Baroda project. You do see here the spillway, the head regulators, and the channel of Ghazi Baroda project. I'll post the details on the LMS about the things that you have to do in this particular assignment. You have to relate the things that we looked into, or the structures that we looked into, and you have to identify them in this particular project. And then you can also consult other materials on the internet about the design features of all these structures. So this would be it for this particular lecture, and see you in the next week, inshallah. Assalamu alaikum.